Welcome back. In this video, we're going to continue Chapter 23 on electronic structure of molecules. And we're going to continue with this idea of constructing molecular orbitals from a linear combination of atomic orbitals. And that idea worked pretty well for diatomic molecules, where we imagine the molecules coming in and the s and p orbitals were constructively and destructively interfering to form bonding and antibonding orbitals. But now we come to an issue where if we want to describe polyatomic molecules, where we have a central atom and multiple bonds sticking out of that one central atom, how do we deal with the construction of those molecular orbitals? And this was an issue that was addressed early in the development of quantum mechanics by Linus Pauling. Now, to understand this, let's go back to the VSEPR model. If you remember this valence shell electron pair repulsion model that you learned in general chemistry. And you learned in that picture that if you had a central atom and it had a number of bonds sticking out of it, if you wanted to get the geometry of that central atom, the bonds sticking out of that central atom, you had to count not just the bonds sticking out, but also the lone pairs that were sticking off that central atom. So you counted the atoms and the lone pairs, and then you looked at that count, and then you decided, well, if there were a total of 2 electron pairs, pairs being either bonding pairs or lone pairs, then you would have a linear configuration around the central atom. If you had 3, you had trigonal planar. If you had 4 pairs coming off, it would be tetrahedral. If you had 5, trigonal bipyramidal. And if you had 6, it would be octahedral. And when you look at these configurations, well, you can imagine very easily how our picture that we've developed so far could describe what's going on here. But what about here, where you have bonds that are sticking out 120 degrees apart from each other? Or in this tetrahedral case, where they're about 109 degrees apart from each other. So that picture where we're just using atomic orbitals sort of as they were given to us when we solved the hydrogen atom, S and P, Px, Py, Pz, and so on, doesn't seem to kind of lend itself to these kind of weird geometries, or to not simple geometries. So the idea that Pauling came up with in 1931 was to construct hybrid atomic orbitals. So to take the atomic orbitals that were on an atom and hybridize them in such a way that when those 2 atoms came together, the hybrid orbital on atom A and the hybrid orbitals on atom B would overlap really well and allow you to form these type of configurations that we saw here in this particular VSEPR model. So, for example, what's called the sp3 hybridization, again, something you probably remember from organic chemistry, is composed of one s orbital and 3 p orbitals. So you take the s and 3 p orbitals, atomic orbitals, on an atom, and you hybridize those to form 4 hybrid orbitals, which can then form better molecular orbitals when that atom comes together with another atom. So you would construct this then. Imagine these are the wave functions for s, px, py, and pz with yet to be determined coefficients for constructing these 4, 1, 2, 3, 4 hybrid orbitals for the sp3 configuration. Now, let's just start simple with, say, the sp configuration. So for beryllium hydride, you can imagine that if you want to do a linear arrangement around beryllium here, you could do a better job of constructing your atomic orbitals that have better overlap in making your molecular orbital by making atomic hybrid orbitals that consist of a mixture of s and p on the beryllium. So if you do that, then you can construct this linear combination, and if you make sure that your orbitals are normalized and orthogonal, and in this case these 2 bonds are equivalent, so we can take A1 and A2 for the 2 different, there's going to be there's going to be sp orbital here and sp orbital here, so that's 1 and 2. So for both of those, we'll assume that they have the same coefficients. So we'll say A1 is equal to A2 and B1 is equal to B2, and we'll construct this set of normal, orthogonal, and equivalent hybrid orbitals on the beryllium. And these hybrid orbitals, and you can see here I'm constructing them, are going to have this kind of shape here. So you can see that when you take the s and the p orbital, you create a hybrid orbital which has much better, bigger lobe here, so to speak, that will then overlap better with the s orbital on a hydrogen as the hydrogen comes in on this side. Similarly, if you construct the other hybrid orbital, then you can see it creates a lobe that's 120 degrees away, which if a hydrogen is coming up here, it will have a much better overlap there. And this simple approach is the way we sort of modify the atomic orbitals before we create the linear combination of atomic orbitals, or linear combination of hybrid atomic orbitals. So if you take BH3, now we need 3 hybrid orbitals, and they need to be 120 degrees apart. So we're going to take one s and 2 p's. So we're going to take an s orbital and px and py with some linear combination that's going to give us this particular configuration. And again, using the same approach as before, making them normalized, orthogonal, and equivalent, we can get these combinations. And when you sort of construct these orbitals, you can see that you have the s and px and py coming together. And in one case, there's 0 for the py component. And you see you get 3 hybrid orbitals, which have nice big lobes that will point along 0, 120, and 240 to bond with those 3 hydrogen atoms around the beryllium. Once again, with sp3, you should remember from your organic chemistry class, we're going to use an s and 3 p orbitals, px, py, and pz, and we'll have some linear combination here. If these bonds are all equivalent, then the coefficients can all be set so that easily determined here to be these values here. I'm not going to draw pictures for those, but you can see this is what the combination that will give you these 109-degree angles between all of those atomic orbitals sticking out of carbon, so it can form better molecular orbitals with the 1s orbitals, atomic orbitals on hydrogen. You can continue with this approach with the trigonal bipyramidal or the octahedral. In that case, you're going to have to bring in d orbitals in your hybridization approach. And I'm not going to write out for the trigonal bipyramidal, but for octahedral, I've given you out here are the coefficients that you need for combining the s, the p's, and dx squared minus y squared and dz squared together to get these 6 hybrid atomic orbitals, which can then form better molecular orbitals in this case. Okay, if you want to sort of summarize this, this is something you probably still remember from high school chemistry, that these are the hybridizations here, but now you see the underlying wave functions, the hybridized wave functions that are made in order to form better molecular orbitals. And I guess the last thing I'll tell you here is that you also remember this from organic chemistry, is that you can have a combination of hybrid atomic orbitals and then just your regular orbitals. So for example, in ethylene, you're going to have, you have 120 degrees here approximately, so you're going to use sp2 hybrid orbitals on each of the carbons, and that will form a nice sigma bond between the carbons and to each of the hydrogens that are out here. But then you additionally can have a pi bond for, there will be a p orbital sticking out of each of the carbon out of the plane here, and those will come together to form a pi bond. So that actually is how the double bond in ethylene is made. It's made from one sigma bond between the carbons and then a pi bond between the pz orbitals of those carbons. Okay. So I think that's it for this video, and the next video we're going to continue and start looking at term symbols for molecules.